Good afternoon, Professor.
Good afternoon, Amy. Oh, and she even went. Wow, how'd that happen? That was cool. Okay, good afternoon, and Ice Cube, and good afternoon. Okay, I'm gonna do it now. Good afternoon, David Khan. Good afternoon, Jamalet. Good afternoon, Chloe. Good afternoon, Diana. Good afternoon, Steven. And he didn't say from 2D today. Uh-oh, maybe he's in 4D today. Well, okay, sorry. I almost made it a stupid joke. Okay, I'm going back to the chat. Wait, no, lots of people are coming in. Where's hello, chat? Oh, okay. Right. So good afternoon, Stephen. Good afternoon, Gianna. Excuse me. Good afternoon, Brooke. Um, and good afternoon, Jalen. Brooke and Jalen, who are getting used to these ridiculous routines. Good afternoon, Shakia. Same thing. Good afternoon, Ashley. Good afternoon. Oh, good afternoon, Board. I really thought I fixed this. Hold on 1 second, because I really want to do physics today. I know it's strange. Oh, it really lost it. Hold on. Sorry. You know the difference between a monologue and a dialogue? Yeah, evidently neither do I. Okay. Good afternoon, Samuel, book 1 or 2, depending on who's reading it. Good afternoon, Jasmine. Good afternoon, Shamil. Good also good after hello, Sarah. Top of the afternoon, Abdel. He remained true to character today. Good afternoon, Brianna. Where is my okay, wait 1 second. Oh, good afternoon, Sam. Wait, that is so funny. But actually, Samuel Book Admin finally fixed his. No, oh, I shouldn't say that. No, it's in the Google Classroom where his name is funny. Okay, yeah, or no, you did fix your thing, Sam. All right, I'm gonna stop talking. But duly noted that it doesn't say AJ anymore if that's where it said it. Just when I learn it, then he helps me out. Okay. Or maybe that's what, all right. I'm just going to get the board back. Okay. And yes. Direct chat person. And there's only one of you right now. So if I'm saying direct chat, it's you. Yes. Thank you. Totally understand. Totally appreciate. And that's very minor. I mean, I appreciate you telling me that's, yes, I'll try to, cool. Thank you. A direct chat person. Okay. Thank you for telling me. Okay. Wait. Oh no! Other direct, sorry, other direct chat person about the monologue and dialogue. No, I mean no. Thank you. That is funny, and you should definitely submit that for class participation. No, I was totally joking because I talk to myself in front of you all the time. I do know that a monologue is one person, dialogue is two, but I'm just saying because I'm constantly muttering to myself, so you'd think that I don't know that, but that's funny. And thank you. Actually, okay, here we go again with the monologue. Oh, LMAO. Oh, and interesting. Okay. Now LMAO is something I did not know what that meant until both of my sons at different points had to explain it to me. And of course, the fact that one of them is a college student, that's fine. But one of them is 8. When he explained something went wrong when he explained LMAO to me. But no, the funny thing about monologue dialogue, I'll say this too. Here's a slightly more subtle thing that you guys might or might not remember from literature class or English class or Shakespeare class or something. The different, so yeah, monologue is one person speaking, dialogue is 2 people speaking with each other. And yes, and I'm joking, and the direct chat person is joking. I mean, okay, but that's true. But here's a subtle thing: the difference between a monologue and a soliloquy, right? Because you've heard of those both in Shakespeare plays or whatever. I know you do science, but occasionally you read, right? What's the difference between a monologue and and I'm not asking because we do have to move on, but I'm just saying, interesting factoid, the difference between a monologue and a soliloquy, at least in Elizabethan times, was that they're each spoken by one person. Wait, someone's here. A monologue is, a speech given by one person. A soliloquy is a speech given by one person. But at least if it's in the context of a Elizabethan play or something like that, a monologue is given by one person while there's a bunch of people around, listening or present, like State of the Union address or something like that. But a soliloquy is something given by one person when there's no one else on stage, when they're just talking to themselves, like Hamlet, to be or not to be, or something like that. So the real question is whether I ever know the difference between a monologue or a soliloquy, because hello, get out of my head. Okay, but anyway, that's all silliness. I'm glad you're all here. Oh, did I say hello to? I think I said hello to everybody. I mean, I'm looking at yeah, I think I said hello. If I didn't say hello to you, it was not on purpose or intentional. I certainly said hello to everybody in the chat. I'm looking at everybody in the, okay, no one's showing video today. I understand it's a bad hair day for me too. Okay. Every day is a bad hair. Okay. Someone, you know what? You think this is crazy? Someone in the live class, in the in-person class on Tuesday, someone who's getting to know me after actually referred to me as unhinged. I mean, can you believe? I mean, I am so unhinged. I mean, really? I totally do not deny it. Okay. I had to look it up, but okay. Seriously, thank you, Sam. Yes, I'm going to tell her or him that you said that. Yes. Oof. Wow. Oh, wait, maybe unhinged is worse than I think. Maybe what's even worse is that I'm not repeating it in public. I mean, yeah, I guess literally it's pretty bad. I don't think they literally. All right, now I'm scared. Okay. And I'm also proving her or his point, and it was totally a her. Okay. Let's do some physics. Because I don't think I have any. You can still keep turning in. I've noticed a couple people have turned in revisions or updates or like more work on their original homework 1B. You can still do that. Wait, sorry. If anybody who turned in a revision of any kind automatically got more points, it's kind of just like that. Some people still turned it in. You will notice that now there's a new homework that is due next Wednesday, not Monday, but Wednesday. There is a new homework. It doesn't mean it's too late still for things to happen on this first one. It doesn't mean that, but it does mean we're moving on. So there's another same thing though, just do your best for your first attempt and then take it from there. The next homework is more on sort of math that we need for this course that we're sort of doing right now. Entirely, actually. Okay. What I want to do now is get back to what we were saying yesterday, what we were saying Monday. Oof. I can't believe someone just wrote oof. Okay. The last thing we said, but stop me, of course, if there's any questions or anything like that. Okay. Well, okay. So this is back to what I am. Okay. So I'm going back. Again, this is all sort of in the context of questions 4 and 5 and beyond in the homework. This is all about work and energy conservation. I'm cycling back, to try to actually really establish what work really is in a more precise mathematical sense. Okay. And the thing we're trying to establish here, my goal by the end of today, by the middle of today, I'm trying to ultimately show that that work, the physics concept of work, is defined to be what is mathematically known as a path integral. I'm ultimately trying to show that work is the path integral of force, okay? And specifically, what a path integral is in math is the integral of a dot product with respect to displacement. So I'm trying to show that work is an integral of a dot product with respect to displacement. Like specifically, I'm trying to show that work is the path integral of force, which means that work is the integral of force dotted with displacement. That's what I'm trying to show. Okay. So I'm trying to link the math together with the physics. And again, for all of you, some of you might think what I'm trying to show really what work really is, and I'm using math to really show you what the physics concept of work is. But for many of you, maybe most of you, what I'm really secretly trying to do is use a physical example called work to really try to get you, perhaps for the first time, or to really try to get you to actually see what this underlying math tool known as an integral really is. Okay, so you can look at it either way. Either I'm using math to explain physics, or I'm using physics to explain math. Whatever you can get out of it, great. But I'm trying to prove that work, or I'm trying to show that work is a path integral of force. Now, where we left off yesterday, Monday, we had already first established that a work over a small amount of displacement is defined to be what's written right here. Like we had already established that if you push or pull an object over a small but finite amount of displacement, delta x, then the dot product of your force with your small but finite amount of displacement will yield what we call, this overall product will yield what we call a little bit of a small but finite amount of work. Okay, we're defining it that way. That's a definition. Sorry, that's a triple equal sign. That's what we established 2 days ago. And it took us a while because we first had to explain what a dot product was. But we did that. It's the scalar product of two vectors. Now, what I'm saying is that okay, so I'm backing up a little bit on yesterday. On Monday, I'm saying now. So this up here in red is the definition of a small amount of work. It's the definition of work, but it only works, it only applies or is reasonable as long as you're exerting a force throughout a small but finite amount of displacement. Small but finite. Now, then we said Monday, well, what do we mean by small? What do you mean this only works if the displacement is small? What the heck does small mean? Good question. And it doesn't mean a number. It's a contextual thing. What small means is, we said on Monday, we said small enough. We mean when we say that delta x is small but finite, so we're using the delta symbol. What we mean is, well, small but finite means big enough to be measurable or calculable or countable, big enough that it's bigger than zero, and it's measurable, but small enough that F, the force, magnitude, and direction can hold steady, hold constant throughout the interval of delta x. That's what we mean by small enough. So this definition worked if the delta x was that small. But we want a general, universally usable definition of work. We want a definition of work that applies even when the displacement gets really large. In other words, even when F starts varying, particularly if it starts varying as a function of X. So what do we do? What we do is deploy the concept of superposition. We say that superposition is a concept that applies to forces and particularly work. Superposition Okay, so first thing, so I'm going a little, just backing up on this. So we're going to apply, in order to get work done over a large interval of space, we're going to say, you know what, if we know how to calculate the work for a small interval, in order to calculate the work for a big interval, can we just like divide the big interval into a bunch of smaller pieces and add them all up? And the answer is yes, we totally can. And that's totally what we're going to do. But I do want to make a slight pause on that and just point out that is totally true. That's what we're going to do. We're going to say, as long as we know how to compute the work over here, and as long as we know how to compute the work over here, and as long as we know how to compute the work over here, like which we do because we have this definition to dot product, and as long as we know how to compute the work over here, then to compute the work for all throughout all of here, we're just going to add up all those segments. That's totally what we're going to do. It is that simple and straightforward. But I do want to point out, it's kind of nice that we can do that. To do that means that we believe that the whole is equal to the sum of its independent parts. Just as a note, that's a nice ability to do that. The reason we give it a fancy name and call it superposition meaning the concept that the whole is equal to the sum of its independent parts, is that, in fact, there are many cases, definitely in life, but even in physics, where this is not the case. You might, like, it's really powerful. And when it's true, it's really true. But it's not always true that the whole is equal to the sum of its independent parts, because it's not always true that the bunch of parts that together come together to make a whole are independent of one another. Just to be clear for a quick second, like sometimes there's a part and then there's another, and sometimes the parts each make a contribution to the whole, but the fact that there are parts sitting next to other parts the parts start interacting with each other. And the fact that there's more than one of them affects the whole. Sometimes the whole is equal to either more than or less than the sum of its parts. And we're going to see that later in physics. When that happens, so I mean, a quick example in life, I always say this, but a quick example in life is like, say I can grade 5 papers in an hour, and say Professor Walters, or in your, say Professor Walters can grade 10 papers in an hour. Okay, if superposition applies, that means if we sit together in a room and grade papers for an hour, I would grade 5, she would grade 10. If superposition applies, that would mean we would grade 15 papers every hour. But the fact is, in real life, if Professor Walters and I sit in a room together and start grading papers, the fact we're not going to grade at the same rate as if we were by ourselves. If we're in the room together, we're going to start talking to each other and either distract each other or maybe give each other tips and tricks and help each other along. So we're going to interfere with each other, either destructively or constructively. So even though there's parts that are adding together to make a whole, the parts are not independent. They're interacting with each other. So sometimes, and in this course, like with waves, that happens. Here it does not. So here we can say there's no interference among these parts. There's superposition. So the whole is equal to the sum of its parts. So we're going to say here, okay, if you want to know the work throughout a whole large interval, even if the forces are changing, what you do is you divide the whole interval into a bunch of equally small displacements, divide it down to a small enough level that for each displacement, there is one constant applicable force. And so you go like, all right, first I'm going to look at the first 5 meters. Oh, the force is 100 newtons. Okay, 100 times 5, that's 500 joules. Put that in my bag. Then I go to the next 5 meters. Oh, here the force is 200. So I do 200 newtons times 5 meters. That's 1,000 joules. I put that in my bag. Then I go to the next and I just add them all up. So in principle, the first thing we do is we say, fine, if you want a big amount of work, we would say divide, we would say this. Well, we would say what I just said. Oh, sorry, that's not what I meant to do. I mean, it's almost what I meant to do, but. Right. So what we would do is, okay. Now, what we would do is use this fancy piece of notation. Now, don't be intimidated by this fancy piece of notation. It is just that, a fancy piece of notation. What, in fact, okay. I mean, you've seen this in math before, right? That big capital Greek letter sigma is a jagged, pointy, unsmooth kind of letter that, or kind of symbol that is sigma, and it stands for sum. And we use it when we are summing up, when we're adding up a bunch of things, right? That's all it means is add up. And the count, the whole I equals 1 n thing just means, okay, we're going to use sigma when we're adding up a bunch of stuff, as long as we're adding up a bunch of stuff that is separable. That is what we call in math or in physics discrete. That means you can, that means each piece has a defined boundary that separates it from the next piece. That means the number of pieces is, even if it's very large, is countable. We use sigma when we are summing up a bunch of countable pieces. I, lowercase I, is the counter index, right? So we just, and I know you've seen this before, and we're not going to go crazy with it, but I really just, my whole plea in all this is that this stuff all actually makes sense. It's not arbitrary black magic. Sigma means you're going to set a counter, the counter of I, called I, at 1. You're going to go to the first delta x, the first 5-meter interval that you're looking at, right? The first small displacement. And how small are these displacements that you've divided up? They're small. You've taken your huge displacement and divided it into little displacements. Maybe they're 5 meters, maybe they're 2 meters, maybe they're 1 meter, but they're all equal, and they're all small enough sizes such that each one of them has one constant force acting on it, right? Not the same as the next force, but one throughout that little interval. So you go to so you set I equals 1, you go to the first little 5-meter chunk, and you ask yourself, okay, what's the force applying to this chunk? The first force. Oh, the first force is 100 newtons. So you do the procedure. You multiply the 100 newtons by the delta x, the 5 meters, and you throw it in your bag, just like I just said, right? Then you set the counter to 2. So you go to number 2. You go to the next delta x. Notice again, I don't put eyes on the delta x. I mean, you could, but I'm not putting eyes on the delta x because each delta x has the same size. They're all the same size. But I go to the next delta x that has the next force number 2. Now that's 200 newtons or whatever. So I dot those together. I put that in my bag, and I keep walking until I equals n. N supposedly, presumably, is the total number of all these chunks that I divide and work into. Okay, so this would be the definition of work for a large displacement, large enough that F is changing. And this works. This is how you can get work, and this would be done. Work would be the sum. In other words, total work is the sum of lots of partial little works. But the only catch, you can see where this is going, I think. The problem is this works as long as the force is changing in discrete, countable, subdividable, divisible leaps like a cartoon. This works if you were to make a graph like a force as a function of displacement. This works as long as the force is acting like a step function, if you know what I'm saying. Right, so let me write that down. What I'm saying here is that realistically, in most examples, such as our spring mass system, the force doesn't change in chunks like that. Like this would work if life were a cartoon. If in 5 meters the force were blah, and then the next 5 meters the force were blah, and then the next 5 meters the force were blah. But that's not what generally happens. What generally happens is force changes smoothly. Generally, force varies as a continuous function of position. Quick sidebar. There's a huge link between, like, the word continuous comes up a lot in calculus, and continuous function as a phrase comes up a lot in calculus. The more I think, I remember when I took calculus, at least the first like 50 times, like the first couple of times, anytime the professor said continue, I mean, I'm just remembering this now. Whenever they used to say continuous function, my head would just fog over and I would stop paying attention. There was something about the phrase continuous function that sounded so fancy and esoteric that something, if I heard continuous function, my brain would say, oh, the professor's getting into like math that's more advanced than I can deal with right now. He's talking to the math people. She's talking to the math people. It's getting mathy. I don't know what they mean by continuous function. I'm out. Like mentally, I would do that. Not really consciously, but I would. I just want to tell you right now, don't get bogged down. Continuous function is not a mathy abstract term. When I say continuous, what I mean by continuous is smooth. What I mean by, well, I'll write it right now. What I mean by continuous right? What I mean by continuous is that if you divide it, I mean infinitely divisible. I mean like water as opposed to sand. I mean, or at least the way we experience water on the macroscopic level. I mean, like, if you were to look at this displacement, you first you look at it, uh-oh, the force is changing. Let me divide it into 5 meter chunks and hope that for each 5 meter chunk, the force is not changing. But then you look, you're like, oh crap, even at a 5 meter chunk, the force started off 100 newtons and then it ended up 110 newtons. So you're like, okay, crap, I better go down to a 2 meter chunk. Let me see, 2 meter chunk. Is that small enough to keep? Is that small enough to keep the force from changing. And then you look at 2 meters like, oh no, I mean, the force didn't change as much. The force only changed from 100 newtons to 102 newtons, but it still changed. So then you divide smaller. And you keep dividing smaller, but no matter how much you divide, you never get to a bounded countable chunk. No matter how small you divide, the force is still smoothly, it's always changing a little bit because so that would be an example of a continuous force function. Continuous literally means no matter how much you divide it, you never get to a boundary. You never get to a piece that you can separate from the next piece. So you can never divide it. That's what continuous means. It means infinitely divisible, or I suppose infinitely indivisible. And it's not a coincidence. Whenever we're doing calculus, they always stop and they say this thing of like, oh, but we need to, assuming that blah, blah, blah is a continuous function. The whole point is continuous means infinitely small, and calculus is all about the infinitely small. I mean, continuous means that the chunks, the subdivisions are infinitely small. And that's what calculus is all about, infinity. So I don't know if that helps anybody or whatever, but so I'm saying if the force is varying all the time, like no matter how small down you go, you're still getting a force that's like you'd have to go down to an infinitesimal length, an infinitesimal displacement in order to catch the force at one number. That's what we mean by continuous. Well, that's what we want to do here. We want the sum of all of the dot products of force with displacement. We want, like, work is in total is the sum of all the dot products taken over little intervals, each of which has one constant number that we can plug in for force. But in most general cases where the force is continuous, we realize, yeah, that's what we want. We want the sum of all the little products. But how little do the products need to be in order for this to work? They need to be infinitely little, apparently, right? If the force is continuously changing, then the little intervals that we need to look at to catch the force before it changes have to be infinitely small. So when F varies, when F, the force, that's an F. When the force vector varies as a continuous function of delta x, we need to take our sum to the limit as delta x approaches 0, right? I'm not saying we know how. Don't get ahead of me. I'm not saying I know how to do that. I'm just saying that's what I need to picture. If I want the full amount of work done by a spring, like a spring exerts one force over here when x is 0.15, but then it exerts a different force over here when x is 0.14. And the fact that, so it changed in that one little millimeter. And the fact is, even if I separate down to the millimeter level, I know that like no matter what number I plug in into f equals negative kx, no matter what number I plug in, it's going to yield a different f. F is changing throughout all the possible values of x. So in order to get the full work that a spring does from year to year, I'd have to add up all the little bits of x all the way, and each one of them dot with, each one of those little delta x's, I'd have to dot with its corresponding f. And each one of those delta x's, if I want to do this accurately, better be infinitely close to 0. Not literally 0, because then there's no delta x at all. I'm not multiplying anything, but just as close to 0 it can be, just enough below the threshold of measurement so that I can't measure any wiggle or wobble or change in the corresponding value of f. So what I want we want to take that sum to the limit. Now, I'm not, hold on. Right? If we want an accurate computation of the total work done in a situation where delta x is big enough that f varies as a continuous function of delta x, then what we'd want, if we want to compute the work done by f, by the changing f over this whole thing, again, for example, a spring, what we want is the sum of all the dot products of f delta x, take it to the limit as the displacement over which each one of those dot products is acting is arbitrarily close to zero. I am not saying I know how to do that. I'm just asking you to, in fact, I'm going to hold on a second. I'm going to change the view for a second. I think this is important enough. Put us, now let's look, that's a heavy piece of mathematical notation I just wrote at the bottom. In fact, I'm going to write it again on the next, hold on. I'm going to write it again on the next page. And I'm going to ask you something. I'm saying that would be the true definition of work over, that would be a definition of work that would work for all cases. Is what I'm saying. I am not saying I know how to compute that. I am saying that that's a large piece of math, or that's a many pieces of mathematical notation, that if I didn't know anything, or if I didn't have this whole discussion, or if I just walked in right now, I might be very intimidated looking at all those symbols. I mean, I think it's fair to be very intimidated looking at all those symbols. But what I want to ask you, and especially if I looked at all those symbols, and I thought that someone was saying to me that I need to know how to actually calculate whatever that thing is, that would be intimidating. I'm not, but what I want right now, I'm going to pause. I want to know if I'm not asking you to compute that yet, if I'm not saying we know how to compute it, because I'm not saying I know how to compute that yet, but I want to know, raise your electronic hand or somehow send me a signal if it makes sense to you why, if we could compute that, that would be what we mean by work. Like, does this definition make sense to you? Thank you, Gianna. That was fast. That was awesome. Thank you, Ashley. Thank you, Chloe. Thank you, Sarah. Thank you. Thank you, Diana. Thank you, Abdel. Thank you. I love this part. I don't know why. Thank you, Amy, Kanina. Ice Cube. Thank you, Jalen. Thank you. Thank you. Wow. Okay. Awesome. Awesome. And of course, now we're getting to the realm where and you're being honest. Yes. Okay. And stop. Good. I know I didn't mention everybody's name, but thank you, Samuel. Thank you, Samuel. Thank you, Jada. I totally see you. Thank you. And all of you who just raised your hand right now, totally, this counts as class participation. You could totally put it in the thing. And by the way, those of you, because I'm trying to, keep up with those, many of you like submit a class participation thing where you'll say something like, today I said hello in the chat, but I also showed avatar, and I also an avatar, and I also like use my voice for 1 minute or whatever, which is all great. But which is very great, honestly, if you ever submit anything and I write on the bottom double dip, that's not a criticism. I hope everybody's clear on this. If I write on one of your participation things double dip, that is totally the opposite of a criticism. What I'm saying is, you've told me at least one more piece of information on this thing here that I can give you more points for, as long as you submit it in the corresponding portal. And the flip side of this, I'm not going to give you, like, I'm too, whatever, you need to submit these things. But if I ever say double dip, it means you've just told me something that should get you even more points. If you take 2 more minutes to find out, like you've shown avatar, and there's a portal for that. Okay. So that's just saying there's more points coming your way. But just like, in Animal Crossing, like you have to submit your Nook miles to get your Nook miles. It's the same thing here or whatever. Okay. Now, good. I'm going to assume that you guys are being honest. I appreciate that you all just told me that. Oh, and thank you, Sam. Okay. So you just put your hand on the thing. Okay. So now here's what I want to say. If it makes sense what I've just said, like that work is just the sum of a bunch of little works, then I'm going to say, and please, and maybe I did that also. Please, if you've been tuning, this is a moment to tune in as best as you can. And again, I know it's very hard to tune into Zoom and we all float in and out mentally. I totally get that. But if you're to choose your moments, tune in now for like a minute or two, because I just made a leap from the top to the, I just made a leap. Well, in fact, let me do this even better. Wait. I am saying, but to me, this is a big, I mean, it's not a leap. It's, I just took a step, but it's a very big step. I'm saying, hello. I am saying, oh, is that a question? No. I am saying that this is literally what an integral is. Okay, I'm about to start using integrals now. I know you've seen integrals in calculus before, but I'm not saying now everybody take out their old memories and their old knowledges of integrals and let's apply them here and let's connect this to, no, I'm saying this is what an integral is. I'm saying if you may have solved a million integrals in your life, but never quite known what you were doing or how to set them up or why or what they meant, then this is the discussion for you. I'm still not yet saying how to solve an integral. That is not my point yet. Sorry. My point right now is not anything about how to solve an integral. Anything you remember about U substitutions or I don't know, power rules or integration by parts. Don't worry about that for the moment. I mean, if you know it, that's great. That'll be helpful. But right now, I'm just trying to establish what the heck an integral actually is, why it ever comes up in math or physics in the first place. And what I'm telling you is, and I'm trying to use the notation in a way not to intimidate you, but to show you that the notation itself actually makes sense. I am saying that we use capital sigma. We use capital sigma to mean sum. And in the context that we're here, the physics context we're in right now, we're summing up a bunch of little products. In fact, wait, I'm even going to, hold on, I'm going to write one more thing. Hold on, pardon me before I forget. 1 second. Bear with me. Whoop. Okay, I am saying here we have a situation where we're adding up a bunch of countable, divisible products. We're looking at a little interval, and more right, we're looking at a little interval of space. We're asking what is the force that applies to that space. We're multiplying them two together, throwing it in our bag, and then walking to the next space. Asking what is the force that applies to that space, multiplying the two together, throwing it in our bag, walking to the next, etc. We're summing up a bunch of products. Like that's what we're trying to do in physics right now. Summing up a countable, divisible collection of products. If you think about it even more specifically, if you think about it in more general terms, go all the way down to the bottom of the page, go to the blue part in the bottom of the page. On the right-hand side, notice that not like I'm saying force and displacement because I'm a physicist. But the key point in this whole discussion is that we're assuming force somehow depends on displacement, or specifically if displacement is a little interval between two positions, force depends on position. Force, we're talking about force times space, and we specifically are assuming that force is a function of where you are in space. Like space is the input, force is the output, right? So we are being asked here, I'm looking at the blue at the bottom of the page. Look at the blue at the bottom of the page. I'm saying that our procedure was that we look at a little bit of independent variable, ask what is the dependent variable that applies there, like look at a little bit of space, as our input, plug it in. Oh, the output, the force for the, so it's like as in F equals negative kx, right? You look at a little x, you plug it in, you get F. You multiply the input by the output, you throw it in your bag. Then you go to the next little realm of input. You multiply the input by the output, you put it in your bag, and you go all the way through. And we summed it all up, and we used this jagged symbol called a sigma to mean sum. What I'm saying is that if we take that to the limit, if we exactly do that procedure, but we make the little displacements, or more specific, more generally, if we make the little intervals of independent variable, the little intervals of x, whatever x might stand for, input, any kind of input, if we take it to the limit where those things are arbitrarily close to 0 in size, right? Then we would, the limit of delta x as delta x approaches 0 is what we call dx, right? If we go to the limit, then the delta x becomes so small that it becomes an infinitesimal or an infinitely small interval called dx. So dx is being multiplied by f of x, and the limit thing goes away. And now all we've done by doing that, if we go to the limit where delta x approaches 0, and instead we therefore substitute the notation dx, if we do that, we're still taking a sum of products, but now our sum is a continuous sum. So we throw out the jagged, pointy sigma symbol, and instead we put in a new symbol that still stands for sum, but is a nice smooth S. Okay, no problem. Okay, no problem. Thank you, direct type person. We take out the sigma, which means jagged, discrete, choppy, countable sum, and we swap in a smooth S for sum, and we say we're no longer counting with an index. We're no longer counting this delta x, the next delta x, the next, because there's nothing to count anymore. All the delta x's are now smoothly attached to one another. So we just start over here at the first value of x, and we start walking, and we walk a little infinitesimal bit of x. We ask, what is the force, or in general, what is the function, the output of x right there? We multiply the two together. We multiply the amount, the infinitesimal amount of meters by whatever the corresponding force is to that infinitesimal amount of meters. We multiply them together. We throw them in our bag, and then we walk to the next infinitesimal step in space or along the x-axis of some general function, like whatever this is. And again, so we do the same thing we've been doing this whole day. We go a little step along the input variable, multiply that size of that input variable step by the output variable, in this case, displacement and force. We multiply them together, throw them in a bag, go to the next, multiply them together, throw them in a bag, go to the next, multiply them together, throw in the bag. And what we have at the end of the day, either way, with whatever notation we're using, we have a sum of products, and specifically here dot products, but whatever. We have a sum of products. The products are the product of space along an input variable times the very output variable that it generates. So products of x by whatever function of x. What we're talking about here is a sum of products. But as long as the sum is continuous, that means we've gone to the limit where delta x has become a dx. So the new symbol that we use to mean sum when it is a continuous smooth is a long, continuous, smooth, flowy S. That integral symbol is an S. I didn't know that until I did. And it's like all fancified now, but it's an S, and it's just swapping in for the sigma. But the sigma was jagged because we were counting pieces. And this thing is smooth because we're just going. But either way, it just, so what I'm saying in English what I'm saying about work as a concept, a physics concept, but I'm also saying as a mathematical thing, what I'm saying, hold on, let me just write this. I'm saying, well, I'm going to say on the next page, the integral is the continuous sum of products. Always. This is what an integral is. It is just a continuous sum of little products. And the products are always between an infinitesimal interval along an independent variable, in this case, x, in this case, space, with the corresponding value of dependent variable. It's all, and every single integral is a continuous sum of products, and each product is simply input times corresponding output. That's what an integral is. And the reason there's always like a dx or a dy or whatever in an integral package is it's not just like math weirdness. I mean, it is weird, but the dx or the dy or the dz that's always in an integral is there because it just means delta x or delta y or delta z taken to the limit. It's there because what the integral is really saying is I want you to walk along the path of the x-axis, and each little infinitesimal step you take along the x-axis, multiply the size of that step by the whatever variable is depending on that step. In this case, in the case of work, you're going to multiply the length of each step in meters by the corresponding force measured in newtons. So the integral of f dx, of f dotted with dx, is work. Work is the continuous sum of all the little forces being dotted with all the little displacements. Now, I'm going to stop first. Again, I'm trying to say two things. I'm sorry. Hold on. I'm going to say one more thing, and I'm going to pause. Sorry. Okay. So again, I'm saying, and I will pause first in a second, I'm saying an integral, from here on in, again, I haven't said one thing about how to calculate an integral yet. I have not. And I don't want you to think about that from there, because that's what all gets, you either get intimidated, well, I either get intimidated when I think about how to calculate integrals, or I get a false sense of confidence, because since I do know how to calculate some integrals, then I think that's what they mean. That has nothing to do with what integrals mean. What an integral is just a sum. It's a sum of products. It's a continuous sum of products. That's what an integral is. We set up integrals and we think about integrals whenever we're thinking about big wholes that we believe we can divide down into smaller parts. Okay, that's what an integral is. Specifically, now the integral that we're talking about here, the integral that is work, I'm saying work specifically is the path integral of force. A path integral specifically means that you're taking a continuous sum of a bunch of products, but specifically those products are dot products. Like whenever we say path integral, a path integral means an integral of a dot product, okay? And specifically the dot product is always between the function itself, the dependent variable, in this case force, dotted with some infinitesimal interval of literal space, like with x, like as in advancement along an x-axis of space. In other words, a path integral is you're looking at a path integral of a certain function or a certain quantity, a certain measurement. When you talk about the path integral of it, you're talking about the accumulated effect of that measurement throughout or over some one-dimensional region of space, i.e. over some path, some length. So a path integral of f is always the integral of the dot product of f with delta x. Now I'm going to pause for, okay, sorry, someone's in the chat and things are happening because my view is bad. 1 second. And I do want to pause for a second. That's a lot. Hold on. Wait, something's in the chat. Oh, yeah. Okay. What's that? Sorry. Okay. Well, okay. In theory, I'm teaching you what work is right now with calculus terminology. In my heart, what I really hope is, at least for some of you, hopefully some of you, if you've had an open mind or you've been listening to this at all, hopefully for some of you, maybe you understand what an integral is in general a little bit better. And the idea behind everything I'm saying right now, I know I'm going in a funny order or whatever. I'm trying to show you what an integral is. I'm telling you that I took at least 3 courses in calculus and at least 2 courses in physics. And I knew the whole, until at least 3 courses of calculus and 2 courses of physics. And the whole while I knew I was totally faking it whenever it came to integrals. I hated them. Anytime integrals came up, I would either run or I would slog through, but I knew the minute integrals were coming up, I did not know what I was doing. And I was a physics major. Okay. I mean, like I was signing up for that crap. And I'm not saying that you're in that position. Everybody's in a different position, but I am saying that it's never too, but eventually it sank in with me what the heck an integral was. Now, when I say eventually, I mean, to be frank, probably 10 years into teaching. I mean, it's not an immediate thing. Well, maybe that's an exaggeration, but what I'm trying to say right now is that this is what an integral is. And put another way, the easiest for me to this day, when I picture what an integral is, the way I picture it, the way I try to understand the math of it is I picture what it needs to compute work, like to picture and the product of force with displacement. Frankly, also, let me tell you that since I'm trying to teach path integrals now, that means that intertwined in this whole discussion over the last 2 days, I've been trying to teach you dot product. The truth is that's 2 different ideas. I mean, not all integrals are path integrals. You don't need to, if you are sort of following what I'm saying, you don't need to also follow the dot product thing in order to follow the integral thing. It is 2 ideas that I'm putting together. An integral is just a continuous sum, of products. The best way to picture it, I think, is to picture work in physics. Okay, that's number 1, what I'm saying right now. And really the best way, or one of the best ways to understand what an integral is unto itself, to know when and how to set one up, because really that's the difficulty. I know in math class, we can get tests And I'm not saying this to disparage, I mean, there's a whole different agenda in a math class, but I know we can get exams where they give us certain integrals and we've learned certain rules so we can solve certain integrals. That's fine. And some of you may be a lot better at that than I was at this stage. I mean, I couldn't even do that sometimes, like solve the integrals. But even when one can, I just want to remind you that like that's when they're already being presented. The hard part is like, why did it come up in the first place, or where, or what? And even if I know it's supposed to come up, how do I set it up? This is how. Okay, you start with a finite product and then you take it to the limit. So this is what an integral is. This is what the work integral is. Oh, sorry, but it's really important if you want to understand this to separate this from the idea of how you solve it. None of this says that an integral is solvable. Like all of what I just said would be true. Even if there was no method for actually computing one, it would still be a piece of notation that, in other words, work is the integral of force with respect to displacement, whether or not we can actually solve it. How do we solve an integral? Okay, that's a different question. Well, I'm just looking at the view here. Wait, sorry, I'm going to do this one more time. Can you just raise your electronic hand if you're basically still with me so far, like more or less, if you're still with me? Awesome, awesome, awesome. Thank you. Thank you, Abdel. Thank you, Sam. Thank you, Sam. Thank you, Gianna. Thank you, Amy. Thank you, Brooke. Thank you, Ashley. Thank you, Diana. Thank you, Jada. Thank you, Jalen. Thank you, Stephen, Brooke, Diana. Awesome. Jalen, I know I've missed some people because it's going fast, but thank you. Okay, awesome. We're going to take that so that you're with me. And again, please, if you're not, remember, I just put up 2 new things in the, if you want me to go faster or slower, let me know. Like, I'm just making my best guess as to where we all are mentally. And the worst thing is I'm basing my guesses of where you think about this for a minute. This is the horror. I'm basing my guess about where you guys are mentally based on like where I was at various points in my like learning career. So I'm projecting my own personality on you. How scary and insulting is that? I don't think you want that. I think the idea that I would assume that you are me is like pretty, I mean, I don't think you're unhinged, any of you. So if you want to actually have me teach you the way you need to learn, you might want to let me know that you're not me. Okay. So where am I going with this? 12 minutes. Quick choice. Hold on one thing. Okay. Well, who's here? So. Okay, that is not how you spell puzzle piecing, but okay. Okay. Again, I want to emphasize everything I just said was triple equal sign. I'm telling you what an integral is, and I'm telling you that work is a path integral of force. It doesn't tell you at all how to solve it. How do we solve integrals? How do we compute integrals? First thing I want to say is, and this is where just to, if you ever felt like you sort of understood derivatives and differentiation, but you were had more of a hard time with integrals, you are not alone, and you are definitely not crazy. There's a reason. Integrals are fundamentally hard. They don't just come next after derivatives. They are intrinsically harder because derivatives, there's always a procedure. Any function that is differentiable, there's like you can look at it, know that it's differentiable, and then there's a way of differentiating it. It's like an algorithm. It is an algorithm. Integration is not that way. Not all integrals are solvable at all. Most are not. The ones that are solvable by different methods for different integrals. There's not one way. It's not linear. It's not an algorithm. And you can't always just tell by looking at an integral whether it is solvable or by what method. To solve integrals does involve puzzle piecing, puzzles, like reverse engineering and experience and techniques. It's not, it seems very much not like math when you're first getting used to math. It's not a forward-thinking process. So if you ever struggle with it, it's not you. It is harder. Integrals, but there are ways of addressing integrals, and there's a couple things I want to tell you right now, and I know we have 9 minutes. Sorry. First of all, this may be obvious to many people. Let's get it straight right from the get-go. The definition of an integral is a sum, right? It is a sum, a continuous sum. So if you just integrate dx, that means we're adding up a whole bunch of little infinitesimal fractions of x. Like to integrate from x1 to x2, dx literally just means, by everything I just said, it just means take a little step along the, start at value x1, take a little step along the x-axis, infinitesimal step, throw the size of that step into your bag, like multiply it by the number 1. Okay, I should be really clear, sorry. To be technical, the integral of dx would equal the integral of 1 times dx, right? Like the function, this would assume that the function of x is just literally the number 1. Now that's a function, constant function, 1. It means like whatever value you plug in for x, you get out the number 1. That's a very, very trivial function. But it's like, let's start with the simplest case. The simplest case is if your function is just 1, if you just, then the rule says you take a little step along the x-axis, you take the amount of that step in meters, you multiply by the number 1, you throw it in your bag. Then you take the next step, multiply that infinitesimal number of meters by the number 1, throw it in your bag. So, and you've started at the value of x1, you walk all the way until you get to the value x2, and you add up all those little infinitesimal chunks of this displacement from x1 to x2. So what do you get? When you add up a bunch of little fractions of x, you get the whole x by definition, right? To integrate is to add up the little pieces and get the whole. So the integral of dx is x. Now this is a definite integral. It means it told you started at value x1, you go all the way to value x2. So it's the total amount of x evaluated. Oh, sorry, it's supposed to be an x2. Evaluated from x1 to x2. That literally means, as you know from class, plug in the value of x2, subtract from it the value of x1. There's your answer, right? Basically, I'm just saying again, integral means the whole is equal to the sum of its parts. If you sum up all of the parts, each of which is equal to 1, what you get is literally the whole equal to 1. Okay, just note that. Most integrals, of course, are harder than that, right? But well, okay, most integrals are harder than that. But what do we do to deal with many of them? And this is, we're going to end. I know we have 4 minutes. Yeah, we're going to end with this, but this is super important also. So observation number 2, the integral from x1 to x2, just using what I just used before, of dy dx. Okay, now you know what dy dx is, right? Dy dx by definition means the limit as delta x approaches 0 of delta y over delta x. You know what that is, right? That means slope taken to the limit, the slope of some line connecting 2 points on a graph taken to the limit where the 2 points are arbitrarily close to one another, right? You know what this is. It's the derivative, right? Just by our notation, right? You know dy over dx, if all assuming that y equals some function of x, dy over dx is delta y over delta x taken to the limit. It's the slope of the tangent line. It's the rate of change in the limit as we were just looking at one point. It's how quickly a graph is changing, not between 2 points, but in the limit as we just look at one point, the derivative, right? Well, look, I'm saying if we have some function, y equals f of x, if we take the integral of the derivative of that function, right, we're going to get the dx's are going to cancel out. Remember, a derivative is a ratio of differentials. The rules of multiplication still work, even though they sort of have to be proven rigorously that they do, but they do. So I'm saying the integral of the derivative of some function equals the function itself. What am I trying to say? I'm saying what's known as the fundamental theorem of calculus. I'm saying that if you just look at the notation we're using, I don't know how to integrate in general, but it seems to me that for some strange reason, the integral of the derivative of some function yields the function itself. So that means when you do an integral, you're unwinding, you're inverting a derivative. This says evidently, this is the fundamental theorem of calculus. Evidently, the integral double equal sign, not triple. We're about to end on this. Evidently, from what I just did, the integral is the antiderivative. That's not its definition. What the integral means is it's a continuous sum of products. But evidently, whenever you integrate the derivative of a function, you get back to the original function. So evidently, when you integrate, you are doing derivatives backwards. It's not what you mean to do. That's not what you're asking about. But evidently, right? So the integral is defined to be the continuous sum of products. But what it turns out to be, this is why it's called the fundamental theorem of calculus. It's fundamental, but it's a theorem. It's not a definition. What the integral turns out to be is the inverse operation of derivatives. Who knew that the area under the curve somehow is the slope of the tangent line backwards? I didn't see that coming, but it did come. So what does that mean with 1 minute left of class? It means that for a lot of functions that we don't know how to integrate, all we have to do is ask ourselves, all we have to do is do a derivative backwards. For a function like negative kx dx, if you want to know the integral and therefore the work done by the spring, you just ask yourself, what function would have given me negative kx if I had differentiated it? So you do the derivative backwards and you get 1f kx squared. I'm not going to write that down now, but I'm just saying the way. So what an integral is, I know we're done, but I'm putting down the cannoli and putting down the gun. But what an integral is a continuous sum of products, such as work is the integral of force with respect to displacement. But how do you solve an integral? You realize that the integral turns out to be the antiderivative. So to solve an integral, you do derivatives backwards. It doesn't always work, but it often works, and it certainly will work here. Okay, that's a lot for today. Hopefully that helped some people somehow, some way. There's more homework due next week. I'll see you. I'm staying if there's any quick questions. But other than that, have a nice day. Sorry to keep you. I love you all in a totally mathematical way. Remember not. Wait, okay. Okay.
Thank you, Professor. Have a great day.
Thank you. Have a great day. You too. Okay. Whew. Have a nice day. Yes. Have a great day. Have a great. Oh, yeah. Wait. Look. Wait. Let me see your. I see your question. No, it's not. You totally still have time. That's what I'm trying to say. You could still totally work on homework 1. It is not too late. I mean, we are moving on to homework 2, but I will still accept things about homework 1. It is not too late. A good question. Oh, sorry. I guess you now know who asked, but yeah. Yes, no problem. No problem. Thank you. Okay, cool. Okay. And are you there? Oh, smile. Oh, smile. Going once, going twice. Going once, going twice. Oh, smile. Going once, going twice. Going once, going twice. Okay, it's been a pleasure. Tune in next week for closed path integrals and why they're called conservative when they yield 0.